So today we're going to talk about time domain reflectometers, TDRs. Before we get started, I would just say that I've worked with the cable products for quite a long time, but what I haven't done for a long time is webinars. So I'll be a little bit rough here, but I'll try to get the points across, and we'll try to have time to answer questions. TDRs, time domain reflectometers, there's a lot of different types of TDRs and different applications and methods. This webinar is going to focus on a specific type and application, basically using a TDR on a primary medium voltage cable, specifically cable fault location is what we're going to focus on. So we're talking about a TDR that would be connected to a cable like this, a medium voltage cable. There's a center conductor and some type of shield, some type of neutral concentric. These particular TDRs come in different flavors. There's three-phase, there's single-phase, there's standalone, there's integrated. If we look at the nomenclature for TDR, starting with T for time, the time is just how long did it take for the TDR's pulse to travel down the cable and back. Domain, unlike a radar or TDR out at an airport, whose domain is air, the domain of these particular TDRs is the pulses traveling down the cable's insulation. In essence, the pulse is trapped between the center conductor and the neutral. We'll get into it later, but these TDRs require two parallel metal conductors, and whatever is between those two parallel metal conductors is the domain. Reflectometer, some of the TDR's outgoing pulse will reflect back from impedance changes between the center conductor and the neutral. The ABCs of our particular type TDR, the TDR pulse board generates a high frequency, low voltage pulse. Typically these pulses are in the 20, 25, 30 volt range. This pulse then will travel down our medium voltage cable. As stated before, it's trapped between the center conductor and neutral concentric. Some of the pulse will reflect back from any substantial impedance change along the cable. And all the remaining pulse is going to reflect back from the far end. And with a pre-known propagation velocity setting, the TDR will display and calculate distances to these impedance changes. Okay, so what does all that mean? Here we have a TDR connected to a medium voltage cable. And, you know, it's not shown clearly, but this cable, the neutral concentrics are grounded at each end, and the TDR is actually connected to the neutral concentric and the center conductor. This particular medium voltage cable has a splice in it. So the TDR is going to release a low voltage pulse when we tell it to. The pulse is traveling down the cable and reflecting back. And in the middle of the screen, you can see this blue line. That's the trace or the impedance signature that we would actually see on the display of the TDR. And what we're interested in is we can see a reflection off the splice, and we can see a reflection off the far end of the cable. And also over here on the left-hand side, I didn't circle it, but this is a reflection off of the splice right here at the connection point. I would call this the characteristic hookup impedance. There's always a bit of bump up, bump down on the left-hand side of your display screen. Okay, here's a picture of a real trace, and you can see here there's a splice, the reflection off the far end. Over here on the left-hand side, it's kind of chopped out of the display picture. It's been slid off to the side, but a characteristic hookup impedance. And also in this, you can see where we've put a marker, a cursor, if you will, that shows the distance to this bump up. So the end of this cable was at 549 feet. Okay, one of the common things that's done with TDR is to verify that you are actually seeing all the way through to the end of the cable. It's pretty easy to verify this. You can simply go to the far end of the cable and ground the center conductor.